When we talk about the evolution of artificial intelligence beyond language, one of the most transformative developments is the emergence of multimodal generative AI. Traditionally, AI systems were designed to operate within a single modality. A model would either process text, or images, or audio, but rarely all of them together in a unified way. This separation created boundaries in capability. Humans, however, naturally integrate multiple forms of information. We read text, interpret images, understand tone in speech, and connect all of these signals into a coherent understanding of the world. Multimodal generative AI aims to replicate this integrated perception and generation capability within machine systems. At its core, multimodal AI refers to models that can both understand and generate across different types of data, such as text, images, audio, and video. The generative aspect adds another dimension, enabling these systems not only to interpret inputs but also to create new content that spans across modalities. This means a single system can take a textual prompt and generate an image, convert that image into a video sequence, add synchronized audio, and even produce a narrative description or dialogue. The key idea is that all these forms of information are no longer treated as isolated silos, but as interconnected representations within a shared model. To understand how this is possible, we need to look at how different modalities are represented internally. In modern AI systems, all data is ultimately transformed into numerical representations, often referred to as embeddings. Whether it is a word, a pixel, or an audio waveform, the model encodes it into a high-dimensional vector space. The breakthrough in multimodal systems comes from learning a shared representation space where different modalities can coexist and be mapped to one another. For example, the concept of a dog can be represented in a way that aligns text descriptions, images of dogs, and even the sound of barking within a similar region of this space. This shared representation enables cross-modal reasoning and generation. A model can take a text description and find the corresponding visual features to generate an image. It can analyze an image and produce a textual caption. It can listen to audio and generate subtitles or even synthesize a related video. The alignment between modalities is learned through large-scale training on datasets that contain paired or correlated data, such as images with captions, videos with audio tracks, or transcripts aligned with speech recordings. Architecturally, multimodal generative AI builds upon the same foundations as large language models, particularly transformer-based architectures. Transformers are well suited for this task because they can process sequences of tokens, and with the right encoding, tokens can represent elements from any modality. For text, tokens are words or subwords. For images, tokens can represent patches of pixels. For audio, tokens may represent segments of the waveform or spectral features. By unifying these representations into a common token-based framework, transformers can attend across modalities, learning relationships between them. One of the key challenges in multimodal systems is the difference in structure and scale between modalities. Text is discrete and sequential, images are spatial and high-dimensional, audio is continuous and temporal, and video combines both spatial and temporal complexity. Designing models that can effectively handle these differences while maintaining efficiency is a significant engineering challenge. Techniques such as modality-specific encoders, cross-attention mechanisms, and hierarchical representations are used to address these issues. Cross-attention is particularly important in multimodal generation. It allows the model to focus on relevant parts of one modality while generating another. For example, when generating a caption for an image, the model attends to different regions of the image while producing each word. Similarly, when generating video from text, the model must align temporal sequences with narrative structure, ensuring that visual elements evolve consistently over time. Another important concept is conditioning. In generative AI, conditioning refers to guiding the output based on specific inputs. In a multimodal context, conditioning can involve one or more modalities. A model might generate an image conditioned on a text prompt, or generate audio conditioned on both text and visual cues. The richness of conditioning inputs directly influences the quality and relevance of the generated output. When we look at practical applications, the impact of multimodal generative AI becomes very tangible. One of the most exciting areas is content creation. AI systems can now generate images from text descriptions, create videos from scripts, and even produce full multimedia experiences that combine visuals, sound, and narrative. This has profound implications for industries such as film, gaming, marketing, and education. Consider the idea of AI-generated films. A user could provide a high-level description of a story, including characters, setting, and plot. The system could then generate scenes, animate characters, create dialogue, and produce background music, all in a coherent and synchronized way. While current systems are not yet at the level of full-length, high-quality film production, the trajectory is clearly moving in that direction. The ability to rapidly prototype visual narratives is already transforming creative workflows. In design and engineering, multimodal AI can assist in creating prototypes. A designer might describe a product in natural language, and the system could generate visual concepts, simulate interactions, and even suggest improvements based on functional requirements. This reduces the gap between ideation and visualization, enabling faster iteration and more collaborative design processes. Interactive educational content is another powerful application. Traditional educational materials are often static, but multimodal AI can create dynamic, personalized learning experiences. For example, a system could generate explanatory videos tailored to a student's level of understanding, combine text explanations with visual diagrams, and include interactive elements that respond to the learner's input. This creates a more engaging and effective learning environment. In accessibility, multimodal AI plays a crucial role by bridging different forms of communication. It can convert speech to text, generate descriptive captions for images, and translate between languages in both text and audio formats. This helps make digital content more inclusive for people with disabilities and those who speak different languages. Despite these advancements, there are significant challenges that need to be addressed. One of the main issues is data. Training multimodal models requires large datasets that are properly aligned across modalities. Collecting and curating such data is expensive and complex. Misalignment or bias in the data can lead to incorrect or misleading outputs. Another challenge is evaluation. Unlike text-only models, where outputs can be compared to reference answers, evaluating multimodal outputs is more subjective. How do we measure the quality of a generated video or the coherence between audio and visuals? Developing reliable metrics for multimodal generation is an ongoing area of research. Computational cost is also a major factor. Multimodal models are typically larger and more complex than single-modality models, requiring significant computational resources for training and inference. Optimizing these models for efficiency without sacrificing performance is critical for widespread adoption. There are also important ethical considerations. The ability to generate realistic images, audio, and video raises concerns about misinformation, deepfakes, and content authenticity. Ensuring that these technologies are used responsibly involves implementing safeguards, such as watermarking, content verification, and usage policies. From a system design perspective, integrating multimodal capabilities into applications requires careful orchestration. It is not enough to have a powerful model, the system must manage inputs and outputs across different modalities, ensure synchronization, and provide a seamless user experience. This often involves combining multiple models and services into a cohesive pipeline. Looking ahead, the future of multimodal generative AI is likely to involve even deeper integration and more advanced capabilities. We may see systems that can understand and generate in real time across multiple modalities, enabling applications such as live translation with synchronized audio and video, immersive virtual environments, and fully interactive digital assistants that can see, hear, and respond in a human-like manner. Another emerging direction is the combination of multimodal AI with autonomous agents. An agent that can operate across modalities becomes significantly more powerful. It can interpret visual information, generate reports, communicate through speech, and interact with users in a more natural and intuitive way. This convergence of technologies is likely to define the next generation of AI systems. In conclusion, multimodal generative AI represents a major step forward in the development of artificial intelligence. By combining text, images, audio, and video into unified models, we move closer to systems that can understand and create content in ways that resemble human cognition. The applications are vast, from film and design to education and accessibility, and the potential for innovation is enormous. At the same time, the challenges in data, computation, evaluation, and ethics require careful attention. As we continue to advance this field, the focus will be on building systems that are not only powerful, but also reliable, efficient, and aligned with human values.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.